Okay, so today we're going to look at trigonometric substitutions. There's three key reference triangles that you want to use and refer to when you have an integral where you're going to use this method of trigonometric substitutions with. The first one, I'll draw it out here and go through the steps. Is this right triangle? And for this one, you're going to use the substitution x equals a tangent theta. You can see this by going back to your high school geometry or trigonometry. If you did tan theta, tangent is opposite over adjacent. So here it's opposite, which is x, and adjacent is a. So tan theta is x equals a, and you can rewrite that as I wrote here, x equals a tangent theta. So when you see an integral that has something of the form square root of a squared plus x squared, where a is a constant, basically a number, you're going to use this substitution, x equals a tangent theta. There are other reference triangles. We'll just look at one example today, but the other reference triangles for completeness is here. In this case, x equals a sine theta, and the third one, x a and x squared minus a squared. You take basically the square root of that. You use the substitution x equals a secant theta. Okay, and just as notes, you see you can get, for example, the hypotenuse and the sides of the other triangles as well by just using the Pythagorean theorem. Because say I wanted to find the hypotenuse, I knew tangent theta. I know the x squared plus a squared would be this hypotenuse squared. And then the hypotenuse comes out to this. So if you forget them, you can always draw these reference triangles. Okay, so how can you apply this? An example is evaluate this integral. So you want to look at the denominator. It has 4 square root of 4 plus x squared. You go to your reference triangles. Above, you see that we have basically this first one. We have something with a square root, and we have a squared plus x squared. That corresponds to this square root of 4 plus x squared. We have basically a squared plus x squared, right? In the denominator, x squared is there, a squared here in our case is 4. So a will be 2. So you're going to use the substitution x equals a tangent theta. And a we saw is 2, so we'll be going to use x equals 2 tangent theta. Okay, so now for this, you're going to basically go through a couple steps. You're going to find your substitution. So basically x equals something. Here we're going to say a tangent theta. You need to find out what a is. Then you're going to rewrite the expression in terms of theta and d theta. Then you're going to take the integral, get a result, and finally go back and put the variables back in terms of x. Okay, so we'll follow these steps. Okay, so we had x equals 2 tangent theta. Our integral was here. So we have dx. Okay, so we're going to need to also calculate that. So if we know x is tangent theta, dx is 2 secant squared theta d theta. And for completeness, we know that in this case, our theta is between negative pi over 2 and pi over 2. If you look at this expression, square root of 4 plus x squared, we need to convert that. So this is the same thing as 4 plus, and then x squared is 2 tangent theta squared and taking the square root. And this is equivalent to 4 plus 4 tangent squared theta. Then you can factor out the 4. Okay, and then you use the trig identity that 1 plus tangent squared theta equals secant squared theta. So we have that. And then I want to substitute now into our integral. So basically we have this integral. Dx we saw was 2 secant squared theta d theta. And then we have the square root of 4 secant squared theta for the bottom. So this will give us 2 times the absolute value of secant theta. We see 2 cancels out. And we also note that in our case, we're looking at secant theta. But this is positive for our domain. We have negative pi over 2 less than theta less than pi over 2. So we can rewrite that as secant squared theta d theta over secant theta, which is the same thing as the integral of secant theta d theta. Okay, then you do your integral. This is an indefinite integral. Integral of secant theta d theta is ln of secant theta plus tan theta plus c. Okay, so that's what we get for the integral. And if you notice, going back to the steps, we had x, which we substituted in. We put it in terms of theta and d theta. We did the integral in terms of theta. However, we have to go back, change our variables to x. Okay. So we have here secant theta and tan theta. Earlier, you may remember we had, let's see, x equals 2 tangent theta, right? Basically, you could use this reference triangle that we have above. So let me rewrite it down here. At x equals 2 tangent theta. And we also had, if you want to do x over 2 equals tangent theta. Okay, so that will be what tan theta is. We can substitute it in a second. And then we have secant theta is 1 over cosine of theta. So you can use your triangle. So basically we had this triangle. Okay, so for us, we had tangent theta was opposite x over adjacent, which was a, which is 2 here. This was a here. And then if you want to get cosine theta is adjacent over this hypotenuse. In our hypotenuse, we had square root of a squared plus x squared. You can also use the Pythagorean theorem, and you get 2 squared or 4 plus x squared. So this is our cosine theta. They actually want secant theta, which is 1 over cosine theta. So secant theta would be 4 plus x squared, take the square root of that over 2. So for your final answer, you have to plug in these expressions. So we have basically ln of secant theta, which we said was 4 plus x squared, take the square root of that over 2, plus tangent theta is x over 2 plus c. So this is our final answer for the integral. So I hope that helped. And